this lecture on moments and moment generating function. In short, is called MGF, moment generating function. Now, let x and y are two-dimensional random vector. It is x and y are both random variables, so it is a two-dimensional random vector. It is just two-dimensional random vectors, and let G be a Borel measurable set, Borel measurable function. G be a Borel measurable. We need everything Borel measurable function on R2. It's two-dimensional. Now, what is moment? What is moment? The moment of say first is a discrete type, or it's a discrete type. There is a two different definition for discrete type and for continuous type. So let the joint PMF is Pij, is a joint PMF, is a probability of x equal to xi. Say x takes the values x1, x2, xn, or maybe infinite, countable, or y takes value y1, y2, ya, m, or maybe this way countable. So x equal to xi and y the random vector y variable y equal to yj. This is Pij. We take this as Pij I equal to say 1 to n, or maybe 1 to any natural number, or j may be any natural number, or maybe 1 up to m, which is the finite. Now G be a Borel measurable function from R2 to R. So take two input and give one output. Borel measurable. It's a Borel measurable. Now we have this double series. We have this double series. It's called double series. Sum over ij. If it is finite, no problem. It is a finite. It's only finite sum. If one component is infinite and say j component is finite, then it is just a series. And if the I component is countable, j is finite, is also it's a series. But if it is I and j both are countable, so fix a natural number, then it is a double series. This is called double series. Double series of this Pij into that the G of the xi yj. Remember, this G xi yj is a real number because it is R2 to R. With that probability, then this is defined as expected value of G of xy. G of xy may be x into y, maybe x by y, maybe x square plus y square, something like that. And this series may not exist, may not converge. This series is converge. If it is absolutely converge. So this is called provided. We assume that provided this summation, this double series or double sum Pij, and the mod value of remember the Pij is positive, but that Gij may not be positive. Remember that Gxi xa may not be positive. So that's why you take the mod value. And we know if this is absolutely converged, then you can interchange the term, rearrange the term. If you rearrange the term, then the series will again converge and the converge to the same limit. But if this is not absolutely converge, conditionally converge, then if you rearrange the term, the sum will be different. That's why we have to take this provided this is finite. This is finite. That means this double series converge. Then this is called this summation or this expectation. This is called the expected value of that Gxy. It's called expectation. It's called expectation of that. So that expected that Gxy may be just x, then is the expected value of x. Gxy may be y, then is the expected value of y. It may be xy gxy may be x into y, so it is expected to have x into y. So whatever that, any model measurable function. And what about the continuous case? For the continuous case, this thing is again this defined as expected value of gxy defined like that. It's a double integral. Now it is double integral minus infinity to infinity. Remember that the whole spectrum may not be minus infinity to infinity. That the output of this x and the range of the x and y may be some finite interval, maybe 0 to 1. But we write minus infinity because otherwise it is 0. So if some function is say between 0 to 1, it is non-zero, and other less than 0 and greater than 1, it is just 0, then minus infinity to infinity integration same as infinity to 0 to 1, just integration 0 to 1. So we just write, that's why we write minus infinity to infinity, whatever it is, it may not be a finite interval, still we write there. And the same thing, the module of this, if this is exist, if this doubles, there must be a f of that is joint density, that fxy is a joint density. If this is exist, where this is a joint density, is joint density of joint PDF of x and y. If this integral is finite, then this is actually it's look by the mode of that. So then the expected value of gx y is defined like minus infinity to infinity, minus infinity to infinity, gxy. Now it's no more there, fxy dx dy. So now this is a double integral. Remember, this is a double integral, double Riemann integral, and we need that convergent, and is not only the double integral, it is also an improper integral. So several limits are there. So it needs some double limit, and we need some that double integral thing to find this expected value. Similarly, if this say x1 x2 xn random vector, then we similarly define, if g is a Borel measurable function from Rn to R, then similarly we define the expected value of some g x1 x2 xn, any some Borel measurable function g. Similarly, we can define. Now we are interested in the case where this expected value is some special type of function, but x I to the I and y to the power of k. So we define. So next definition is very important. This is expected value of x, say x to the power j and some y to the power k. What is this? This is this is for a continuous case, some double integral. For discrete case, this is just some double summation. Remember here, this g function is gxy. This function is just x to the power I and y to the power k. So x square, y square, or x square. By the way, that ij are non-negative integers. This belongs to that may be 0. Natural number you name 0. So that may be 0. So j may be 0. So then it is y to the power k just. And this is just defined like m ij, the moment, the ijth moment is also called ijth moment. So then what is m10? It is just expected value of x. What is m01? It is just expected value of y. Similarly, what is just m11? It is just expected value of f into y. Similarly, like that. Next, we define mu jk. Mu jk is just expected value of. Remember, we assume that this is exist. Assume this exists. Existence. If it not exist, we can't define like image. Again, assuming existence of this, this function, it is just x minus expected value of x. This is like a central moment. It is a raw moment. The previous one is raw moment, whole to the power j, and y minus y expecting a y whole to the power k. Assuming this exists, provided exists, the double integral or the double summation exists. Then it is called central moment of order j plus k. It is called central moment of order. Remember, it is not I or j or k, it is order of the order j plus k. Similarly, the previous one is called the raw moment of order j plus k, or moment, just moment. It is called moment of order j plus k. So the variance is the order 2, and that covariance is also order 2. Then j equal to 1, k equal to 1, mu 1 1. And for variance, it is just mu 2 0, or mu 0 2, two different variance of x and variance of y. So this is called covariance. So if you take the mu 1 1, it is just expected value of x minus expectation of x, which is just m10 into that expected y minus expected value of y. Then it is called covariance xy. And covariance divided by the root over variance of x and into root over variance of y is called the correlation coefficient. It's called correlation coefficient. So this is called covariance. This is the, by definition, this is called covariance. This is called covariance. We know this also. This is same as this is actually same as we know in previous lecture that this is nothing but this. This is nothing but this. So it is just m11 minus m10 into m0. Now you can calculate this different type of correlation, covariance and variance. Now the theorem, the most important theorem is this. Theorem is, let x1, x2, xn be random variables such that expected value of that x mod of xi, all the expectation is finite. That we assume for I equal to 1, 2, n variable. And let that a1, a2, an be reals. These are real numbers. And set S, the summation is just a1 x1 is a linear sum, a2 x2 an xn, the linear sum of this random variable. And if this expectation exists, all the x1, x2, xn, then the expected value of s is also exist. And the value is equal to, this expected value is equal to just the sum over I equal to 1 to n ai, and this expectation of xi. Just you can pull the expectation inside the summation. The proof is very easy. For discrete case is easy. You have to just interchange the summation. This, because there is just a finite sum and the expected value is the infinite sum, you can easily interchange that. The two, both the summation is infinite. There is then the interchanging is, there is a problem. There's some need some condition. But here it is just a one thing is finite, another thing is. Similarly, for integration, it's just an integral, one integral and then summation. You can just take the summation inside. See, the summation, just integration f plus g is just integration f plus integration g, because the summation is finite sum, because it's just up to n, the summation up to n. So proof is now easy, and you just take, if you take already, if you take just all this a1, a2, all are 1 by n, then what happens? If all these are all 1 by n, this is called just mu, then mu is just okay. If it's all are 1 by n, then what is s? First of all, what is s? The s is just 1 by, or x1 plus x2 plus dot dot xn by, so it is a mean, sort of mean. Now this expectation exists, then the expectation of s is nothing but just 1 by n sum over I equal to 1 to n expectation of xi. Now if all this expectation are equal, all this expectation of x1 equal to expectation of x2, is all the expectation are equal, all the expression of all the random variables are equal, say equal to mu, then that s, that mean that s is also the, we just that summation, like say, better we write in this form x1 plus x2 plus xn. It's also called x bar, or something called x bar. This is also mean. So this is just scored of the previous theorem. And now, if they are product, what happened the product? What happened if the product is there? And then there is a problem. If you take the product, then what happened? Now the theorem is this: if you take the product, says expect to value the product x1 into x2 into I equal to 1 to n xi. So x1 into x2 is this product of this? Is this product of all this? No, may not be true. We know the expectation of x into y may not be expectation of x into expectation of y, but it is true if they're independent. So let x1, x2 dot 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 xn are independent, be independent random variables, and obviously such that all the expectation exists, such that all this expectation exists, which are finite for I equal to 1 up to n, then this will happen. And this also easy for you know how to prove for the two case. If x and y are independent, you know how to prove this. So if they are independent, the covariance is 0. The covariance is 0. So the what happened? The next theorem is also important. If x and y are two random variables, independent, if they're independent, if and only if, not only if it's independent, something has happened. So if and only if, what happens? For every Borel measurable function, every Borel measurable functions, the two functions say g1 and g2, the expectation of g1x into g2y, say x square into a y cube, like that. It's just the expectation of g1x and expectation of G2. So what is the meaning of that? So if X and Y are independent, then expectation of G1X into G2Y is equal to expectation of G1X into expectation of G2Y. On the other hand, if it is true for all G1, G2, then X and Y are independent. Remember, if expectation of XY is equal to expectation of X into expectation of Y, then XY may not be independent. Covariance is 0 may not be independent. But if all this Borel measure for every Borel measurable function is true, then this is true. Again, just you can see in your book, in the book, so I'm not going to this. This theorem is not easy, but just omit the proof. This result is important. Now, say next theorem is very useful for the different calculation of variance and other thing. So say x1, x2, xn are random variable, may not be that independent, and expected value of that mode of xi, so it is exist. So assuming all this expectation exists for I equal to 1 to n, and a1, a2, an are real, and we write just s equal to just summation I equal to 1 to n ai xi, the variance of that s is nothing but that sum over ai square variance of xi I equal to 1 to n plus the double sum I less than j double sum ai twice ai aj and covariance of xi. Remember that covariance of xy is same as covariance of yj. So this is important, and the proof is just trivial. We know the proof for 2. The variance of x plus y is just variance of x plus variance of y plus twice covariance of xy. Similar, it is like a plus b whole square formula, like that. It is like a plus b plus c whole square form. It's like a square plus b square. So the square part is the variance of the product part, 2ab is the covariance part. So what happened then? Then you can say it's corollary. The next corollary is this: if all these variance are same, all the variance are sigma square for all I, if all the variance are equal, and say it is IID. First of all, say it is IID. We take it as IID. So the corollary is this: so x1, x2, xn are IID independent. So covariance part is 0 with the variance of each xi is same. So it is just take sigma square. No need of taking the mean, the expectation. Then clearly then the variance of that sum over I equal to 1 to n ai xi is just sigma square into the sum over I equal to 1 to n. The variance, all the common variance is ai square. So in particular, variance of that x1 plus x2 plus xn by n, the mean x bar, is just sigma square by n. So all the ai's are 1 by n. So 1 by n square plus 1 by n square up to n terms. So it is 1 by n because the independent part, the covariance part is 0. The next theorem is very useful for some bound or for some maximization or minimization problem. So again, x1, x2 are IID, xn are IID, random variables with common variance sigma square. And let's say a1, a2, an be reals such that the sum over I equal to 1 to n, the I is 1 is also called convex combination. If for any a1, a2, an is for linear combination, we call convex combination. And let s equal to the sum over ai xi, I equal to 1 n, then the variance of s is least, is the minimum, is least if all the ai's are just equal 1 by n. So in next lecture we will prove it. The proof is important here. So this variance of the summation, that x1, x2, xn, the variance of this summation ai xi is least when this actually ai's are 1 by n. So x1 plus x2 plus xn by n. So in this next lecture we will prove it.